Good morning, I'm Kimsey-Miller.
I'm Jewell.
And we studied star spots on LO Pegasi, a variable star in the constellation Pegasus. So stars are balls of plasma, or gas so hot it's been mostly ionized. They're comprised mostly of hydrogen and helium. And in sun-like stars, they generate energy in their core through nuclear fusion. This energy escapes through the radiative zone by radiative diffusion, or just the outward migration due to random motions of photons. Above the radiative zone, we have the convection zone, where convection is the main energy transport. And above that, we have the photosphere, which is generally what people mean when they talk about the surface of the sun. So convection is just hot gas rising and cool gas falling. So in the sun, they form pockets called granules. So hot gas rises in the center and cool gas falls over the sides. These areas last 5 to 10 minutes and they can be 700 kilometers in extent, or about from here to Philadelphia. This big black spot is called the umbra, and it can be 30,000 kilometers in extent, or about a little over 2 Earths fitting side by side right in here. The penumbra, this filament-like structure, and the umbra both make up a sunspot. Sunspots generally last about a month, and if you'll notice, there are no granules in this sunspot region, so that means there's no convection. So sunspots typically come in pairs, and they're connected by great arching magnetic field lines, with the northern magnetic polarity with the magnetic fields pointing out, and the magnetic field lines pointing into the southern magnetic polarity. We can see these magnetic field lines by looking in the far UV because of gas that has been trapped in these magnetic fields, and they greatly resemble a ginormous horseshoe magnet. So our sun rotates west to east, and these sunspots travel along the surface with this rotation. The spot in front is called the leading spot, and the spot in back is called the trailing spot. And in one hemisphere, the leading spots all are of the same magnetic polarity. So south, south, and across the equator, the leading magnetic polarity switch. So north, north. This is known as Hale's polarity law. And approximately every 11 years, the leading magnetic polarities switch hemispheres. So sunspots are dark because they're cooler. Sunspots can be 4,000 Kelvin, while the rest of the photosphere is about 5,800 Kelvin. They're cooler because the magnetic field lines that run through them suppress convection. So this suppression of convection decreases the energy output. So when the sun has lots of sunspots, the decrease in energy output can be as much as 0.1%. When we see sunspots on other stars, we call them star spots. And on stars such as LO Pegasi, these star spots can be extremely massive compared to our own. So that means the decrease in energy output is much more substantial. So the sun's overall magnetic field is about 1 Gauss, while the magnetic field in sunspots can be 3,000 Gauss. These strong magnetic field lines have a lot of magnetic tension in them. So if you imagine stretching a rubber band taut, it's very difficult to move the band sideways. So these strong magnetic fields with their magnetic tension suppress flow of plasma horizontally across them. So this means that convection cells can't form. And the main energy transport is now radiative diffusion, which is less efficient at the surface of the sun. To understand how these strong magnetic fields form, we can look at Faraday's law and Ohm's law. As the resistance goes to 0 around a loop, the EMF goes to 0. This implies that the magnetic flux through the loop is constant. So the magnetic field lines that thread through this loop have to go with this loop as it moves sideways. We call this flux freezing. So as the plasma tries to move through the sun's overall magnetic field, the electrically charged particles in the plasma feel forces from the magnetic field. These electrically charged particles now form electric currents. And these currents generate their own magnetic field. So now we have a net magnetic field that is made up of the sun's overall magnetic field and the induced magnetic field. And it's this overall magnetic field that experiences flux freezing. So as the magnetic field lines move with the plasma, magnetic tension and an isotropic magnetic pressure build up. And it's this magnetic tension that wants to pull these magnetic field lines back to their original position. So you can imagine trying to pluck a guitar string, and the more you pull up on it, the more tension you feel. And now Amanda is going to finish up explaining how star spots form, as well as go over the research that we did over the summer.
So, as we saw before, when a star spot forms, there's usually two ends, like an out end and an in end. And the other question is, why do they form this shape? So if you think of the sun's overall magnetic field as like a series of horizontal flux tubes running through the plasma, when the flux tube comes out of the surface, there will be two spots, like an out end and an in end. So you see the connecting magnetic field lines that you would expect. So the tubes that have very strong magnetic field lines will actually have the plasma within them being less dense than the plasma outside of the flux tubes. So if you think about like a pool noodle, when you hold the two ends underneath the surface of the water, the pool noodle tries to lift up in the middle because the material that makes it up is less dense than the surrounding water. So then tubes that have the strong magnetic fields and are consequently less dense will try to pop up in the middle, like daisies. For our particular research, we went to Perkins Observatory, a few miles off campus, in the smaller of the two telescopes there, right there. And we would go to Perkins to set up at around 10 p.m. and set the telescope to track from about 11 p.m. to 4 in the morning, because that's when Ella Pegasi is best visible. There's a camera attached to the telescope that takes pictures through different light filters on a designated schedule. So the 4 filters that we used are standard for astronomical research. They're called B, V, R, and I, and are blue, visual, red, and infrared. And using these 4 filters actually improves our ability to tell how far north or south the sunspots are on Ella Pegasi. Once the images are taken and processed, we can use something called aperture photometry, where we put these radii around the star to take into account the sky noise in the target star. So this green star is our reference star. It's a known stable magnitude in all 4 of our filters. So we can, and the magnitude is the measure of the star's apparent brightness, or how bright it looks from Earth. And for historical reasons, lower magnitudes are brighter stars and higher magnitudes are dimmer stars. And the 2 red stars are the stars that the program will determine magnitudes for. This one is Ella Pegasi, and this one is our check star to make sure that the reference star is actually doing what we want it to do. And so we collected our data over 3 nights in a row, and so we recorded Ella Pegasi's full rotation, and we're then able to input the data collected through aperture photometry and create a light curve. This is one of our light curves through the B filter. We plotted the magnitude through 1 rotational phase, so we can tell kind of where the star spots are on the surface based on when its magnitude dips and when it rises, since this magnitude scale is flipped and lower magnitudes are higher up. And since star spots are so much dimmer, the minimum here is actually where the star spots are visible on the side of Ella Pegasi pointing towards Earth. These are all 4 of the light curves that we use, and you can see, since all of the vertical axes cover 0.2 magnitude, you can clearly see that there are different amplitudes in the different color filters. And this is what gives us the greatest, or the best way to determine where the star spot is on the surface of Ella Pegasi. We input the light curves that we created into a program designed by Dr. Herman to actually map the star spots on the surface of Ellipagasi. This is our output for this year. It actually involved all four B, V, R, and I light curves, whereas in previous years we only used one or two. And so we just went from this pinpoint in the sky and created a 3D model of what it looks like 81 light years away. Space is cool. What questions do you have?
Questions for Amanda and Brooke?
Hello.
Can you go back one slide to your 3D model? So is the leading spot, does this star rotate west to east as well? Hold on. Or does it rotate east to west with the leading spot on the left? Am I saying that right? Or
We actually can't tell which way it's rotating, due to the fact that if it's rotating this way, it's still going to look the same as to going that way. Does that make sense?
Yeah, so there's a degeneracy, so to speak. In other words, the mirror image of that with the star rotating in the direction is exactly the same light curve. So we're assuming that it rotates left to right there, so the little dip on the side would be the trailing spot. But it could be reversed left to right, you never know.
okay.
Yes.
So you mentioned that this is a variable star. In which way does that affect what you're looking at and why you're looking at it?
Variable star just means that the magnitude changes over time. And so in this case, that variation is due to the star spots, which is what the data we're looking for is. It isn't a pulsar or something. The variation is from the star spots. Yes.
Have you guys had a chance to compare your results from this summer to, like, say, previous years?
We have, actually, and it's pretty interesting because for example, the light curve that they produced last year is pretty much flipped to the light curve that we produced this year. So where the star spot is on the surface of the star is almost 180 from where it was then. I don't know. Yes?
Do you think that star spot moved, or do you think that one went away and a new one came
It's
up?
probably a new star spot, most likely, but there's no hard and fast. Anything else? Yes.
You said that star spots can be way bigger than sunspots. Do you have any idea, roughly how big this spot would be?
Well, do you recall the mass and radius?
So Ellipagasi is a main sequence star. It's a hydrogen burning in its core star like the sun. Its spectral class is estimated as K 3 to 8. And that means that, if I recall correctly, its radius is about 75% that of the sun. So in other words, while the star is a bit smaller than the sun, those spots are way bigger than the sun's spots are.
For reference, if you were living on a planet orbiting Ellipagasi looking at the sun, you wouldn't be able to tell that there were any sunspots ever. While we can actually pretty clearly tell for Ellipagasi.
You need very high precision photometry to detect star spots on the sun because the amplitude variations are a fraction of a percent, whereas this one, 10-20%. It's because it's spinning so rapidly. It has a much stronger so-called magnetic dynamo, so it generates much stronger fields than the sun because it's a so-called young solar analog. The sun probably had big spots like that when it was a baby too. It's calmed down until later. It's midnight. It's just like people, they kind of